Okay. Okay. Hello, everybody. Thank you for being here in such a big number for the last talk of this conference, I think. And thank you for the invitation as well. My name is Ralf Karrenberg. I'm a PhD student at Saarland University at the chair of Sebastian. And I'm going to present our work on improving the performance of OpenCL on CPUs. So let's have a look at a small kernel, an OpenCL kernel. I hope most people can see at least a little bit. This is a discrete cosine transform. And the way this works is essentially, just for those who are not too familiar with OpenCL, the user writes a sequential kernel. So this is Scalar code. And that is executed by a possibly huge number of threads. And the way these threads actually do something different is that they can query their thread ID with calls such as getGlobalID or getLocalID and similar things. We have barrier statements, which we're going to talk about a little bit. And the way this is executed, the execution model, some of you may have seen that before. Every box here is a single thread of the space of threads we have, and they are combined into groups. So you can query, for example, also the group ID and the local IDs inside these groups. And that more or less gives you a natural way of implementing that on a CPU, which could look like this. So you have, that is C code, well, more or less the C code we are using in the CPU driver, which essentially is looping over the groups, and then inside each group loop over the local thread. So you have, this is an example for a 2D kernel, so you have one loop per dimension, basically. And then inside these, you call the scalar kernel, which is supplied by a function pointer, which we get from the LLVM JIT code generator. So the scalar kernel gets a structure with all the arguments and a few parameters like the local IDs and etc. So that is the very naive way of implementing that. And the first thing we do here is we move the innermost loops, the two loops over the local threads, inside the kernel. So essentially, this here is on driver side, and the stuff that is inside the kernel is on LLVM side and gets jitted. So that means we have a barrier here where nothing can be optimized or whatsoever. So what we're doing now is we generate these loops inside the kernel. So we now call a kernel that is not executing one thread or not computing the results of one thread, but of the whole group. And that is the basis for most of the optimizations we are doing then. So, very interesting thing. All you have to do in order to exploit multi-threading, more or less, so it's really not much more, is add this one pragma omp parallel 4 if you're using OpenMP, or do something similar for TVB or whatsoever. So essentially the OpenCL driver we have implemented does exactly that, so nothing more for multi-threading. We focus fully on code generation, optimizations, and vectorization, which is going to be the second part of the talk. So let's have a look at the group kernel. So this is, I decided to go with C code because it's a little more compact than having LLVM IR. So this is actually generated in LLVM IR, but yeah, showing loops is a bit more, needs a bit more space. So this is now the group kernel that we generate. We generate the loops automatically, and we have the old sequential kernel inside, call to that old sequential kernel. And that now can be inlined because that is all inside LLVM, which, if we take the discrete cosine transform, looks a little bit like that. So I tried to compress that a little bit. And now we immediately see that either we on our own or the LLVM optimizer has a little bit possibilities of doing a better job here. Because first of all, this call to get global ID, we can optimize that now by using only local variables or parameters. So I can replace that by an access to the local sizes struct and the multiplication, so we can basically compute the global ID by the local size and the group ID plus the local ID. So that means we can get rid of basically all those callback functions, get local ID, get global ID, and replace them by direct accesses to values. And we also don't have to pass them by parameter from the driver. So very simple optimization, but quite nice already. And then, of course, we can exploit LLVM's optimization. For example, here you see the local ID in Y direction times block width is loop invariant code for the innermost loop. So we can pull that out. Well, LLVM can pull it out if it decides to, of course, so we don't do anything explicit here, but that is one example of what that can do to pull the loops in. Pretty basic stuff, but can have a nice impact. So the problem now is we have this barrier here. And since the barrier in OpenCL forces us to stop execution of every thread of the group at exactly this point, so that means the way this looks now won't work, because we have a loop which executes sequentially, and we have to stop at every thread at the barrier. So what we do for that is kind of similar to what Pablo was just telling you. And I'm going to give you an example of how that works for us. So let's suppose we have this kind of function here. We have 3 barriers in blocks A, C, and D. And to make it a bit more interesting, also barriers inside the loop. First of all, we split the basic blocks at the barriers exactly, and then we create continuations. So what Pablo was referring to, we call these continuations the small functions, because it's kind of similar to continuation passing style for those of you who are familiar with that. So the first function, of course, is f1, and it returns an ID, basically, which means which tells the rest of the kernel which function to execute next. That would be function 2, which looks this way, not very surprising. That calls function, or that returns an ID with function 3. And then the last one is a bit more interesting because it consists of these blocks. So we do introduce some code duplication here, it's very important to note. But essentially, that means that we put all these functions into a big switch statement, which goes into a certain case depending on the last returned ID. So if execution comes here, we return the ID for function 3, the switch statement jumps to function 3, and that is executed then. So the way this works for synchronization then is that around each of these functions, we put the loops over the local threads. It looks like this. This slide is more of a reference, so if you, I'm not going to explain all of that now. Essentially, we have a big while loop. Inside, there's a switch statement which chooses which continuation to execute next. And inside these cases, you have the same loops around the local threads. So that means we execute one continuation for all threads. Then we jump to the next one, loop over the local threads again, and that means we implicitly perform the synchronization without any threads, real threads whatsoever. So let's get to the next part, which is parallelism. So obviously, since OpenCL is a data parallel language, the main source for performance is exploiting parallelism. What you've seen so far was basically everything sequential execution except for the OpenMP thing. So that results in an execution like the one to the right. So if you have a CPU with 4 cores, you can execute 4 threads at once. And now what we're doing is we exploit the SIMD instructions, which means on a CPU with 4 cores and SSE, you would have a SIMD width of 4, and that would allow you to, so we're doing some different vectorization than the basic block vectorization that Hal was talking about yesterday. So we are using every SIMD lane to execute a thread. And that means if we're having SIMD width of 4 and 4 cores, we can execute 16 threads at once. So those of you who have seen the talk of WFVOpenCL last year, I think at the US conference on the Intel OpenCL SDK, they are using a very similar technique, so that might be familiar to you. So let's have a look at how this looks inside LLVM. So now we call a function that is noted here SIMD kernel, and we call that whole function vectorization. We had to take another name because vectorization is so ambiguous that whole function vectorization says what we are doing. We're taking the original scalar function and create a new one, which is not semantically equivalent, which computes the same as 4 threads before it did. So in that case, you can see that the new SIMD kernel gets 4 thread IDs instead of 1 in one dimension, and it computes everything for these 4 threads at once. And the problem with that is diverging control flow, and that is what the rest of the talk is about, because straight line code is boring. So here's the thing that is the main problem with vectorization, with SIMD vectorization in general. So let's suppose we have a control flow graph like the one on the left. So we have a loop and an if statement inside, and on the right you can see traces of different threads that execute this function. So you see that the first 2 threads, for example, one goes to block C and one goes to block D, and the 3rd and 4th thread also iterate the loop once more often than the 2 others. So we have quite a diversity of traces here. And the only way to cope with that in SIMD code is to linearize the whole thing. That means we execute all code and have to make sure that those parts that would have been inactive get blended out. So we use the former condition of the branch as a predicate, and after arriving in block E in this example, we, well, so to say, blend together the values that were coming from both sides of C and D. So this is in general called control flow to data flow conversion. It can be done for essentially all kinds of control flow. So this works on nested loops with multiple exits, whatever. So there's previous work on that stuff. So unfortunately, there's some problems here. So first of all, we have some overhead for maintaining and updating of the predicates, which is, we can't get around that, more or less. We have some overhead for operations with side effects, because if you have a printf on the left side, you don't want to have that printed 4 times, but maybe only 2 times if only 2 of 4 threads are executing that. I'm not going to go into more detail on that. It's not so interesting here. More important is the next 2 points. That is, for example, if you think that block C might be a very large block with lots of computations, very expensive, but it's only executed in 2% of the cases. And then the problem is, if we linearize that, it's always executed, which is obvious that this can give us quite a bad drop in performance. Similarly, the linearization can also increase register pressure. So all the values that were living out of C into E now are live while D is executed. And that means the register pressure in D is increased, which can lead to additional spilling and also decrease performance. And also quite badly, as we've seen in a few benchmarks. So that is a very valid point. Summary would be that this works really good if you have straight line code. But, well, the more control flow you get, the more complicated it becomes. So if we look at the discrete cosine transform again, we see that, well, it's not straight line code. So we have a loop here, and inside the loop we have a ternary operator. On the other hand, the conditions for these control flow statements are actually constant, because they only depend on constant input values like the block width and the inverse. And that means, although this is control flow inside the kernel, all the threads will always go into the same direction in the control flow graph. And that is a fact that we are trying to exploit now. So the idea is to optimize cases where the threads do not diverge, as you can see on the right here. So we have different traces now, and it's always either C or E. Well, the loop is still not uniform, so it's a bit different from the DCT, but at least for the if statement, looks like we can do something there. And the first thing that comes to mind is you can insert dynamic predicates, dynamic predicate tests and branches. So that's a technique that is, I don't know how well known, but to me it's known as BOSC, branch on superword condition code by Shin. That means you test at runtime the mask in block B and see if it's entirely true. Then you can skip, in that case, if it's entirely false, you can skip block C and directly jump to block D, which means you execute less code, so you achieve one of the goals. But since it's still linearized code, you still have the problem with register pressure. So you can't get around that, because it might still be the case that everything is executed. So you still have linearized code. What we are doing now is we're trying to prove statically that a certain branch is always the same for all threads. And that means we can retain the original control flow, or at least certain control flow edges, in order to not have a fully linearized control flow graph, but yeah, like be able to jump around certain blocks. This is, of course, a bit more conservative than the dynamic test, because there might be cases where you have sometimes uniform control flow, so sometimes they are all going in the same direction, but not for all instances of not for all threads. But if you can prove it, you have less executed code in the end, and you have the original register pressure, so you don't increase anything there. So I'm going to try to give you a small, kind of an idea of how the analysis is working. First thing important here is we have a notion of uniform and varying branches. Uniform means that all threads are always going into the left or right direction, so there's no divergence whatsoever. For example, if you have an if statement that checks if the block width is odd or even, which is uniform, it's always the same for all threads, because block width is a constant parameter. And the same if you have that in loop as we have it in the DCT, you know that this loop will always iterate the same amount of time. On the other hand, if you have what we call a varying branch, this means that of all the threads that enter block B, only a fraction goes left and the other part goes right. And that is, for example, the case if you have conditions that depend on the thread ID. So, for example, in that if statement here, it checks if the thread ID is odd or even, and that might be different for different threads, of course. So now with that knowledge, we classify different blocks as either divergent or non-divergent. And just informally, a block is divergent, which is noted by a gray shade on the block. If it's a direct successor of a varying branch, for example, blocks B and C are direct successors of the varying branch in A. And the second criterion is that there might be disjoint paths from the same varying branch that lead to B. So, for example, in block F, you have a path from the false branch in A through blocks C and E to F, and you have different disjunct path from A over the true edge through B and D to F. Might not be entirely clear, but that's the definition, and that is what is working. So there's another one for loops, which I'm going to exclude here because it gets a mess. But essentially what we are doing now, to give you an impression of that, is let's say we have this control flow graph here, and the first thing we do is when we are linearizing that is we order the blocks by data dependencies, so that is just one possible ordering. The naive version now would go ahead and just remove all branches and jump directly to the next one. If you've done a correct job with creating the predicates and the blending code, that is a valid function and will produce correct results. The problem here is that you see the E, the block E, doesn't have a shade. That means it's not divergent, and that means we don't want to execute that. So we want to find a way to produce a linearization that is valid, but does not necessarily always execute E. And that, well, the first thing would be, well, we just retain the edges that lead to E and from E. That would lead us here. The problem with that is now if we execute C and the uniform branch says, okay, we're going to E, and then we jump from E to F. And the problem here is that if there were any threads in A that took the true branch, they want to execute B and D, and they have to execute B and D. But now we took the jump around it, which means we get wrong results. What we have to do is rewire the edges that leave that uniform part to the first divergent block again. Just as kind of an intuition. In that case, we've reached our goal. We have a linearization that is valid, and E is optional. So the block E is not always executed anymore. So let's see how that, if that actually works. And what you see here in that table is a comparison of different configurations of our vector of the OpenCL driver that we have, with different configurations of the whole function vectorization. So the baseline here is sequential execution. So a value of 1.0 would mean that it's exactly as fast as the sequential execution. there's no multi-threading involved whatsoever. So this is just single-threaded, either sequential for 1.0. An ideal speedup would be 4 or even a bit more due to caching effects and stuff like that, because that's an SSE architecture. So you can see immediately that the Naïve implementation can be pretty good. For example, for Black-Scholes, which is mostly straight-line code, it achieves almost the perfect speedup of 4. However, for a large part of the other benchmarks, it's even slower. So we really have to do a lot more here. It's not enough to just plain stupidly linearize everything and vectorize it. We have to do more. The comparison of BOSC shows that, so the second column here is uniform optimizations of uniform expression. So that's sort of a baseline for the dynamic and static divergence analysis. So the BOSC doesn't bring a lot of performance here, even has a bit of overhead for the histogram, which is why the performance actually goes down. Whereas the static divergence analysis in our linearization has quite a nice effect on a few of the benchmarks. So for some, there's simply no uniform control flow, so they can't do the technique can't do anything, so the performance doesn't change. But for example, for the discrete cosine transform that we've seen, performance improves quite dramatically. And most importantly, it's actually faster than the sequential execution, which is probably the most important part. Yeah. However, we still have to say that there is still cases that are just not, or right now not suited for vectorization, or at least not for our algorithms. That is, especially the Floyd-Warshall is mostly dominated by random memory access, and actually decreases quite a lot in performance. So the last table I'm going to show you is a comparison to the Intel and AMD CPU drivers. So this is CPU drivers, very important because many people seem to confuse that. So what you see here is essentially that the driver we have on the benchmarks that we tested is on average 2.5 times faster than the Intel one and around 40 times faster than the AMD one. Which is probably because AMD put more work into the GPU side of stuff and didn't care too much about CPU, but that's only speculation. So the one thing that is a bit confusing maybe is the Floyd-Warshall numbers. And there, I was just talking about that it's probably not very well suited for vectorization. You see here that Intel is doing a very good job with some heuristics. They decide not to vectorize. Which, if you look at the number of our driver to the left, would also be a good idea for us, but we don't have that heuristic right now. So if I switch off vectorization, you can see that the other transformations that we have, for example, are also apparently pretty useful, and the sequential execution is quite fast as well. So these are numbers that include our OpenMP multi-threading scheme plus vectorization utilization of all cores, essentially on a 4-core with SSE. So let's look a little bit at what LLVM is doing for us here. So the one thing that is most important to note is we heavily rely on the JIT code generator, which is a really good decision because we don't have any complaints there. So thanks to everybody who's working on that. It's working pretty well, as the results also show, right? And the other thing is that the IR itself is pretty convenient to use in terms of vector computations, especially since the last patch on vector selects and type legalization, which I'm very glad that people from Intel worked on that and actually pushed it to mainline. The two things that are kind of remaining is the move mask still requires an intrinsic for me. It's just one thing, so that's not too important, I guess. And it would be great to actually have predication in the IR. So some kind of support for predication, because right now we have to maintain the masks ourselves and have some kind of data structure which we can query. So that's a bit ugly. Would be cool to have something, but I think there's some people working on that already. So good news there. As a small outlook, we have a few more ideas for optimizations for the whole function vectorization stuff. So it's likely to get even better a little bit. Integration of the whole stuff inside into the LLVM mainline is a topic. there is certainly some nice applications like combination with the basic block vectorization that Hal talked about yesterday. Or, yeah, you can use the technique in general for classic loop vectorization if you essentially just put the loop body inside a function and call our library. That gives you classic loop vectorization if you do all the loop analysis stuff. And yeah, support for architectures with true predicated execution, like the Larrabee new instruction set, is also on the line. So, small summary. OpenCL benefits from our group kernel-based implementation, so we can optimize uniform expressions and the accesses to get global ID and that stuff. That also enables our continuation-based synchronization scheme. OpenCL benefits a lot from multi-threading, of course, and from the SIMD vectorization stuff, but not if you do it naively, or not always if you do it naively. So the divergence analysis improves that by reducing the amount of executed code and reducing register pressure and overhead if it can prove uniform control flow for certain branches. Yeah, the evaluation showed that it's really important to have some kind of more sophisticated vectorization technique than just plain linearization, because otherwise you just lose performance very often. And yeah, the sources are available, although I should have put a disclaimer here that I think Tobias wrote something like that on the LLVM mailing list sometimes last year about Poly, where he said that it's most likely to rather destroy the world than do you any good, which is probably also the case here. But so if you want to have a look at the code, it's there. Both the code for the vectorization, which is a standalone library, which uses LLVM, and for the OpenCL driver, which uses this library. So it's two different projects, but they use each other. Yeah, by that, I want to thank you for your attention, and I'll be happy to answer any questions.